Okay, so here we go. All right, so like I said, chapter 7 is primarily about work. The only type of energy we're really going to talk about in chapter 7 is kinetic energy. Okay, so we'll deal with potential energy when we get to chapter 8. Okay, so hopefully that keeps things a little bit easier. I found it really tough working through this chapter because there's still going to be problems where things go up and down. And your knee-jerk reaction is going to want to be to think about gravitational potential energy. And I'm going to ask you to kind of try as much as you can to kind of put that on the back burner and try to not use it because it's going to mess you up, okay? All right, so anytime you've got motion, you have to have energy, okay? So a couple things about energy. First of all, it's a scalar, which means it doesn't have direction, right? Okay, it's just quantity, that's it, all right? Sort of an overarching theme of this chapter is going to be the fact that we can change energy from one form to another, and we can transfer it from one object to another. Okay, essentially that's what work is. Work is you converting energy from one form to another, or one object to another. Okay, and then finally, this will really come up in chapter 8. The amount of energy you got in a closed system is always going to stay the same. Okay, something doesn't just magically gain energy. Okay. So anyway, this chapter, like I say, we're really just going to focus on kinetic energy, and we'll talk a little bit about transferring energy through the means of what's called work. Okay. So cool. Cool. All right. So kinetic energy. We're going to just use capital letter K for kinetic energy. I'm going to write KE all the time because I'm so used to doing it. So if I write KE, I mean K. Okay. So any object that's moving has kinetic energy, all right? And you guys hopefully recognize this equation from last year, right? Kinetic energy, it's half of the mass times the velocity squared, all right? Very frequently, you're going to have to work backwards and use the kinetic energy to find the velocity. So if you algebraify this equation, it gives you this. I know you can all do the algebra, but we're going to use this so often that I figured I might as well just throw it up there, okay? It's one of those equations, you're going to use it so often, you're going to memorize it just by virtue of using it so much. Okay. Notice that the kinetic energy depends on two things. It depends on the velocity and on the mass, right? Okay. So when you're looking at how much kinetic energy something has, you have to take into consideration both of those factors. Okay. So if you've got two objects that are going at the same speed or same velocity, that doesn't necessarily mean they have the same kinetic energy, because it also depends on the mass. Okay. The units that we're going to use to measure kinetic energy, or really any kind of energy, are called joules. Notice the spelling, it's J-O-U-L-E, not joule like, fancy jewelry joules. Abbreviation is capital letter J. Okay, and you guys remember, hopefully, that 1 Newton, by definition, is 1 kilogram times a meter per second squared. All right, 1 joule is 1 kilogram times meters squared per second squared. Okay, so right now this is probably a little bit like, what does all of that mean? Some of this will make a little bit more sense once we start learning sort of how these pieces fit together. Yeah. That's how one of the ways you find work. Yeah, so that's where we're headed. And that's why you've got extra. Yeah, work and energy are the same. Okay, everybody good? Okay, and we're getting to all that stuff, so good questions, but no, good questions. All right, so everybody okay with kinetic energy? All right, so I put together a couple, they're really simple examples of just sort of calculating kinetic energy. Partly just because I want you to see how the mass and the velocity affect how much kinetic energy there is. So kind of bear with me. These examples are probably a little silly for an AP class, but like I said, I really want to make sure that we're sort of starting from scratch because I just want to make sure you have all the background here. All right, so here we got Carl the cat and Dave the dog. So here's Carl, here's Dave. All right, so Carl has a mass of 3 kilograms. Dave has a mass of 6 kilograms. They're going for a walk together. They both walk at 4 meters a second, so let's find their kinetic energy. So velocity is 4 meters a second, velocity is 4 meters a second. So they've got the same velocity, they're not going to have the same kinetic energy though, because they have different masses, right? So that's basically the point of this example. So kinetic energy is 1/2 mv squared. So plug in your numbers, your mass is 3, your velocity is 4, you know. So you end up getting 24, and the units do work out, right? So you're going to have kilograms times when you square your velocity, you're going to get meters squared per second squared, so you do get joules. Cool. All right, if you repeat the process over here for Dave the dog, your velocity is the same, but you've got double the mass, right? So you're going to get double the energy, right? So it gives you 48 joules. Cool. All right, so in the next example, Carl gets jealous because Dave has twice as much kinetic energy, right? So he goes, oh, well, I'm going to catch up to him. I'm going to go twice as fast. Will doubling the velocity double the kinetic energy? No, why not? Because of the squared, right? So it's not directly proportional. It's a direct square relationship is what we'd call that. Okay? So here, our mass of Carl is still 3 kilograms, but now our velocity is 8 meters a second. So you end up getting actually 96 joules. So notice, our velocity got multiplied by 2. That means our kinetic energy got multiplied by 2 squared. Cool. Easy peasy, I assume. Everybody good? Cool. All right. Obviously, if the velocity is 0, then your kinetic energy is going to be 0, right? You have to be moving that kinetic energy because kinetic energy is energy of motion. All right. Cool. Too fast? Or are we okay? Too slow? All right. We'll pick up here. All right. Notice you can go backwards. If I give you the kinetic energy and the mass, you can find the velocity, right? So we just talked about this. So here's my mass, it's kilograms. Kinetic energy. See, I did it. There's KE. Sorry. 300 joules. So you can find the velocity. Sorry? Why are we using K instead of KE? Because that's what anything other than a first year physics course uses K. Like, you know, when you take physics to college, they'll use K. So just plug in your numbers. So the idea is this kinetic energy is going to determine the velocity, right? So we're just kind of working backwards here. So you get 2 times 300 joules divided by your mass. Don't forget your square root. So you're going to get square root of 100. So it just gives you 10 meters a second. All right. So the point I'm trying to make here is there's an intrinsic relationship between kinetic energy and velocity for a given object, right? Because your mass for your object isn't usually going to change, right? Unless you've got like a leaky bucket or something like that. Yeah, Alex. Oh, I'm really glad you asked that. So, I'm trying to think if I might have put an example in here about this. So because kinetic energy is a scalar, the direction of your velocity doesn't matter. Okay, so if Dave the dog is, you know, moving at 10 meters a second and he turns and keeps going 10 meters a second, his kinetic energy hasn't changed, even though his velocity changed. Okay, so that v squared is the magnitude of the velocity. Yeah, so this tells us nothing about direction. Good question. All right, everybody good? Okay. All right. Is this? Oh yeah, that's right. Okay, so I put in these questions. This was before the first time we did these. Do we want to do the questions now, or do I want to let you work on them and then we can go over them later? These are the concept-y questions. You guys want to work on these and then we can go over them next time I see you? Is that cool? That way we don't waste time on them now? Okay. The questions here are going to be in a different order than they are on your notes. So you might want to renumber them maybe. So this one is number 1, but the next one gets messed around a little bit. All right, so do these, plan to do them for, say, Tuesday. Okay, we'll take a few minutes and go over them Tuesday. Okay. All right, work. So we're going to use capital letter W for work, okay, which is why we don't use W for weight, right? We use FG for weight. All right. So, like I said at the start of the hour, you can do work to either transfer energy from one form to another, like kinetic to potential or whatever. Kinetic to heat energy is something that comes up. Or you can do work to transfer energy from one object to another. Okay? In order for work to be done, a force has to act on the object as it travels in a direction which is not perpendicular to the force. Okay? So, in other words, oops. How do I want to say this? Okay, here's a person carrying a cake. All right, they're walking this way at a constant velocity. Okay, which way is the person pushing the cake? Upward, right? Okay. There's no force left or right, correct? Because our velocity is constant, or at least no net force, I guess we could say, right? Okay, so here's the force of Roy. Okay, so even though he's sort of going to get tired from holding that thing, technically speaking, according to our physics definition of work, he's not going to be doing work because the force is perpendicular to the direction of motion. Okay? The only way that work is done is if there's at least some component of this force that's not perpendicular. Okay? Yeah. Say that again. He's preventing it from falling, but he's not doing anything to change the energy. He's just maintaining the energy, basically. Okay? So he did work to get it moving. I agree with that. So, like, it was at rest.
So he picked it up.
Correct.
But he's walking at constant velocity.
Right. So, yeah, so if you're struggling a little bit with that, remember, if you're doing work, you've got to be changing energy in some fashion. Right? Is he changing the velocity? No, so he's not changing the kinetic energy. Okay, we haven't learned about it yet, but he's not changing the potential energy because he's not changing the height. Okay, so while he's doing this, he's not doing work. Okay, and it's a little weird, right? Because you're like, he's getting tired. What is it? Right? It doesn't seem like it sort of adds up. But according to the physics definition, he's not doing work because he's not changing the energy. Okay. Okay. So here's how you calculate work. All right, and here's sort of this is why what's the cosine of 90, you guys? Cosine of 90 is 0, right? So to find work, you take the dot product. You guys remember dot products from forever ago? Scalar product. Okay, so you're taking the dot product of force and displacement, really, okay? And remember, dot product is just the magnitude of the two vectors times the cosine of the angle between them. And notice, if the angle between them is 90, you're going to get 0, right? Okay? All right, so let me run through a couple examples here. I don't know if you noticed I skipped question number 2. That will show up later. Okay, so in this example, we've got this, this little block. They call it a bead, whatever. We've got this object that can move horizontally along this little wire here. So all of our motion is going to be on the x-axis, right? And then you've got this force that's being exerted at this angle, right? So if you want, you can take that force that they've called F and you can resolve it into two components. There's an x component and a y component, right? You guys agree with that? That one force F is equivalent to these two forces, Fx and Fy, right? Okay? But Fy is perpendicular to the direction of motion, right? So it's not going to do any work. The only force that's doing any work is the x component. And isn't that just F cosine theta? Follow? Okay, so we're pushing it horizontally with a force equal to Fx, I got you next, through some distance d, right? So this F cosine theta is really just Fx times the distance you push it. Yeah.
So is this one-dimensional?
This example is yes. Well, the motion is one-dimensional, right? Because it's attached to this bead, to this wire. It can only go along the x dimension. I mean, it's the lawnmower thing, right? Like if you push a lawnmower, even though you're pushing down on it, it's not going to move down because the ground is in the way. So the motion is horizontal. Good? Everybody good? Okay. So the idea here, you guys, is, presumably it's not going to move up or down at all, right? So there's going to be a normal force, pushing the bead down, right, to prevent it from moving up or whatever. All of your motion is going to be horizontal. Your net force is going to be horizontal, right? So it's going to gain velocity that way, isn't it? Right, because you've got a net force pushing it forward. Okay, and if you gain velocity, you're gaining kinetic energy. So you're changing energy. That's the work, is the change in kinetic energy. Okay. And this sort of illustrates that, saying, oh, look, at the beginning you've got the small kinetic energy, but because of this force, you're going to gain kinetic energy. So these are like little bar graphs, small kinetic energy, big kinetic energy. Cool? And that kinetic energy changes because of this force changing the velocity. Cool? All right, and notice they drew this little blue vector here to represent the displacement from my starting position to my ending position, right? Cool? Questions? Oh, thank you. Yeah, it's not always. In this example, it's not negative, but it can be. Suppose that, let's see. So simple example. So suppose we had, whatever, a block sliding this way on a frictionless surface. Okay? Maybe it's a school bus that's about to squish a baby. Okay? And then Superman's pushing it this way. Sorry. Didn't we talk about that example? Okay, cool. I'm glad. Otherwise you guys are like, what is he talking about? All right, so here's the force of Superman. All right, so the displacement is going to be this way, positive displacement, but on my x-axis, my force is going to be negative, right? Follow? So the work is going to be negative, which makes sense because aren't we going to lose kinetic energy? Okay, so that loss of kinetic energy is represented by a negative amount of work. Yeah. 100%, yeah. Most of the derivatives that we're going to do are, you're going to do some integrals, where you're going to take the integral of a force versus position graph to get the work. I haven't seen any that are like what you're talking about. We can certainly do stuff like that, though. So, yeah, Alex.
Would this only be like
Say that again.
this only be like angles that are
No, because if they're more than 90, so what would happen? So let's suppose Superman was pushing this way. Oops, I'm going to put that over there. Then, and some of this will come up as we do examples. So let's suppose that this force is, I don't know, arbitrarily, let's just pick some numbers. Say it's 100 newtons. And let's say it's going to move this way through a displacement of, I don't know, whatever, 12 meters, right? Okay. Well, the angle between D and F is more than 90 degrees, right? So here's my D, here's my F. Oops, what did I say, 12 meters? So let's have this angle be, I don't know, let's do 120 degrees, say. Okay. So if you wanted to find the work done, you would do F D cosine theta. So check it out. Watch what happens. My F is 100 newtons. My D is 12 meters. Oops, let me do this. Newtons times 12 meters times the cosine of 120 degrees. Cosine of 120, I think, is negative a half.
Yeah.
Right? So this gives you 100 newtons times 12 meters times negative 0.5. And it manufactures that negative, right?
So then we have to not assign a negative to the force even though it's against the motion.
Well, so how do I want to say this? If you, so there's two ways of solving this.
Take an opposite angle, we should use the force as positive.
Correct.
Okay, so that's what.
Yeah, yeah. But let me say this. There's two ways of solving this. One way is to do what I just did here. The other way to do it would be to replace F with a y component and an x component. If you do it that way, then you'd multiply your x component by your displacement, but your x component would have to be negative, right? You see what I'm saying?
So if you're bringing in components, then F would be negative.
Correct. Follow? All right, are we good? All right, cool. Okay, so here's another example. So this, in your notes, that is not number 2, it's number 3. So where it says number 3, cross it off and put in number 2. Well, I know we're going to go back and renumber that when we get to it. Sorry. I didn't realize until it's my bad. I mean, it doesn't matter. Whatever. Call them whatever you want. It doesn't matter. They're in a different order here than they are on the paper. Okay, everybody good? All right. The only reason I changed the order is because where I've got question number 2 placed, we haven't learned everything to solve it yet, so I had to move it later back. Okay. All right. Now, if multiple forces do work, then the net work or total work is equal to the work done by the net force. So, what the hell does that mean? All right, so here's what I mean. First of all, we're going to use, this is supposed to be W net. Sorry, these notes need some work. So we're not going to use W for net work. We're going to use W net. Okay, so work done by an individual. Okay, all right, so the definition of network is it's the total of all the individual works done. So if you've got like 3 different forces doing work, then your network would be the work done by force 1 plus the work done by force 2 plus the work done by force 3. Okay, so that's what this is saying. My network is the total of each of the individual works done by each of the individual forces. Cool? All right, so work 1, oh, well, that's force 1 times displacement. Work 2 is force 2 times displacement, and work 3 is force 3 times displacement. Dot product, I should be saying, not times. But good? All right, well, you can, because it's dot products, you can sort of factor out a D, and this becomes F1 plus F2 plus F3 dot with D, which is just net force dot D, right? So the point is, when you're finding net work, you can either find your net force and do dot product with distance, or you can find each of the individual works and then add those up. Follow? There's an example of this in a minute, so if I lost you there, hang tight for a minute. Okay? Everybody good though? Okay. All right. So there you go. Another example. All right. So here we go. This we've already alluded to this a bunch. This is what I mean. It's so hard to separate work and energy. So I've already talked about the fact that if you're doing work, you're changing the energy, right? And we talked about like Superman stopping the bus, right? And we said that the work that he did was negative because he's decreasing the kinetic energy. That's this. This is the work kinetic energy theorem. All right. So your net work, you guys, and please make sure that says net work. The net work is your change in kinetic energy. Okay. So if you find the work done by your net force, that tells you how much your kinetic energy changes by. All right. This is super, 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 super valuable for problem solving. Okay. So please make sure you know this, and please make sure you have the word net in here. The net work is the change in kinetic energy. Yeah. No. Because for your kinetic energy to change, your velocity would have to change. And your velocity can't change without motion. Right? Okay. Everybody good? All right. So all of this stuff can be shown, and I found if anybody wants me to, I'm happy to go through the math and kind of show where this comes from. But it's basically this. Look, force causes change in acceleration, right? I'm sorry, force causes acceleration. It causes change in velocity. And that change in velocity results in change in kinetic energy. So anyway, you can do some quick algebra, doing some substitution to show this. The v squareds, kinetic energy is 1/2 mv squared. So it's like 3 or 4 steps of algebra to get from these 2 equations to this. Okay. If you want to see it, hang around after school. Okay. So this is going to be kind of our nuts and bolts for this first homework assignment. Okay. That equation is going to be right there at the center of every problem. Not every problem, but a lot of them. Okay. All right. So let me do 2 examples. This first one is kind of a silly one. The last example, which is not in your notes, but I added this morning when I was looking at these notes, I think is going to be a little bit better. All right, so anyway, this one is basic. So let's start with a basic one, then we'll do one that's a little more involved. All right, so here we go. Carl the cat has a mass of 3 kilograms. They're going for a walk. They walk at 4 meters a second. Carl speeds up to 8 meters a second. He travels 2.5 meters in the time it takes. How much work did static friction do? And then you're finding, I probably should have written the average force of static friction as he speeds up. Okay, so here's what we know. Dave has nothing to do with the problem. So the mass of our cat is 3 kilograms. His initial velocity is 4 meters a second, and then he's going to speed up to a final velocity of 8 meters a second. So notice his kinetic energy is changing, right? Okay, so let's do this. Let's find his initial kinetic energy. Everybody okay with the O's for initial? Okay, so this is going to give us 1/2. The mass is 3 kilograms. Velocity is 4 meters a second squared. So this is 24 joules. We had already figured that out, but there it is again. So at the beginning, he's walking along. He's got 24 joules of kinetic energy. Then he's like, oh no, Dave. And he tries to get as much kinetic energy as Dave. And he ends up with 96 joules. His kinetic energy increased, right? Why? Say it again. Positive work. Good. Yes. What's doing work here, you guys? You can't do work on yourself. Friction, right? When you speed up, you're pushing against the ground with extra force to speed yourself up, right? Okay? This is not really a great example because he's walking, so I should have. This needs some work. But so anyway, so look, you guys, it's okay. It's the math works out. So look, our net work is the change in kinetic energy, right? So let's find our change in kinetic energy. Oh, gotcha. Very good. All right, so our change in kinetic energy. Remember, you guys, anytime you find change in something, it's always final minus initial. Always. Okay? So we're going to do K minus K initial. So that's 96 joules minus the 24 joules he began with. That's a work of 72 joules. So that's part A. How much work did static friction do? Well, remember, the change in kinetic energy is net work, right? Follow? That's the assumption here, yeah. It's an internal force. You need an external force to change the motion of something, or to change the energy of something. It's conservation of energy. It's the sitting in the car, pushing on the dashboard thing. That's why you can, yeah. Sure, yes. Yeah, so like when you push your arm, the action is whatever. Your shoulder's pushing your hand forward. Your hand pushes your shoulder backwards, but you don't move because of friction between your ground.
So does that work?
It's work on a part of your body. Yeah. All right. Remember, you guys, at this point, we're treating every object as a particle anyway. So, all right. So is everybody good with what I did here? This is huge. Notice I used the work kinetic energy theorem, right? I found my change in kinetic energy. That's my net work. Ethan's question is important. We're assuming the only thing doing work here is friction. So this is my net work. Cool? Yeah. All right. Finally, now we can find the average force of static friction. This is sloppy. I really need to rewrite this example. So work net is net force dot displacement, right? So we know our net work is 72 joules. That's got to equal the net force dotted with the distance, which is 2.5 meters. All right, so how do we deal with the fact that this is a dot? I hadn't thought this when I wrote this out, but it doesn't change anything. Which way is friction going to act, you guys? Does it act opposite direction that he moves or same direction that he moves? Same. Just think about what's happening. When you step, you're pushing the ground backwards. and the ground pushes you forwards. The friction is preventing your shoe from sliding backwards. So to prevent your shoe from sliding backwards, it has to push your shoe forward. Okay? It's preventing your foot from sliding backwards by pushing forward. Okay? Remember, you guys, your acceleration is always in the same direction as your net force. If he's accelerating forwards, then the net force has to be forwards. With no exceptions. Like that's acceleration and net force are always in the same direction. Good? Okay. So this actually is F, net force, sorry, times 2.5 times the cosine of 0, right? So, if you just, I wouldn't write that out. I would just recognize, oh, my force and my distance are parallel. So it's just multiplying, right? Make sense or no? Okay, so what do we do? Just divide by 2.5, and your net force ends up being, it's like 28 point something, but with sig digs, it's 29 joules, or 29 newtons, sorry. And again, with Ethan's question, friction's the only force, then there's your force of static friction. Cool? All right. Okay, any problems with it? All right, we have 15 minutes and one more example, which is more than enough time. So let's do that one example. This is not in your notes, so write it down. I realized that we were lacking a really good, like, algebra-y example. No, what did I just get? What's the place? Donut Express, is that right? Donut Express.
30 days ago.
Man, have you had those custard rulers they have? Man. Oh, is that a good thing?
Oh,
Yeah.
2 a.m.
Are we going there at 2 a.m.?
Okay. All right. So this is I like this. This uses a little bit of everything that we just talked about. Okay, and it's not terrible. All right. So what you're going to see is there's actually two ways that you can solve this. You can use Newton's laws in some of our kinematics equations to find the change in kinetic energy to find the work. Or you can do force dot distance. It's so natural for me to say force times distance, so if I say that, I really mean force dot distance. So I'll try to get in the habit of saying that. Okay, I'm still writing. Okay, are we good? All right, so let's draw this thing. So here's the box of donuts, 50 kilograms. It's sitting at rest, so our VO, no, I'm gonna write this, our VO is 0. Roy pushes the box using a force of 400 newtons at 30 degrees below the horizontal. So I'm gonna kind of draw it, well, here, I guess we can just do this. So here's force of Roy, 30 degrees. 400 newtons, right? Okay. He pushes the box 6 meters. So my displacement is 6 meters. All right. So I can find the work done by Roy, right? Because the work done by Roy should be the force done by the force of Roy dot the displacement, right? Okay. So for part A, the work done by Roy is the force of Roy dot the displacement, right? Okay. So for us, the force of Roy, well, so I guess let's do this. So that's F, force of Roy, times the distance, displacement, times the cosine of the theta, right? Make sure you've got the right angle. Yeah? And that's exactly what it is. And I was going to show it that way in a minute. So yeah, you're like 10 seconds ahead of me. Okay, so is everybody good? Okay, so let's do it. So it's 400 newtons times 6 meters times the cosine of 30 degrees. Solve it, and it gives you, it's like 2,078.5 joules, and then I rounded it off to sig digs. 2,078.5 joules. Okay, so is everybody good with A? All right, so B, how much work did friction do? I don't see, unless we were to find the initial and final velocities and find the actual change in kinetic energy, I don't see a way of doing this without finding the force of friction. And I can see the way you're going to have to find the force of friction. So we're going to find the force of friction. All right? So in order to do that, don't I need to take this force and split it up into components? Right? Because I'm going to need to know my normal force. And that normal force is going to be affected by the y component of this guy, right? Follow? So 50 kilograms. So I'm going to take the force of Roy and split it up into components. So here's the force of Roy in the x direction. Here's the force of Roy in the y direction. So the y direction ends up being 200 newtons down. I'm going to put a negative sign on it, just to indicate that it's downward. And the x component ends up being 346 newtons. Don't forget your gravity, negative 490 newtons. It's not moving down, so my normal force has to cancel all of that business. So that's going to be what, positive 690? Am I going too quick, or are we okay? Everybody good? All right, so now I can find my okay, so now I need to find my force of kinetic friction, which is coefficient of kinetic friction times normal force, right? So here's my normal force. Coefficient of kinetic friction is 0.25. So figure it out, and you get 172.5. So let's put that in our drawing. Good? All right, so back to what Ethan was saying before. Now that we've split the force up into components, another way that we could have found the work done by Roy is to take just the horizontal component of his force and multiply it by the distance. And it gives you the exact same answer. All right? And in a lot of ways, I like that better. Okay? Because then I feel like you're understanding, oh, wait a minute, I just want the component of the force that's parallel to the displacement. Whereas I think if you just use FD cosine theta, you can sort of plug numbers in, but not sort of be processing that. You know what I mean? So I will usually actually find the x component, or find, you know, the component and then multiply it by the distance or displacement. Cool? All right. So now I can find the work done by friction. So my force of friction is negative 172.5. My displacement is 6 meters. They're anti-parallel, right? The negative takes care of the anti, right? So we can do part B really easily. Let me shrink my drawing a little bit here. All right, we are almost done. So part B, the work done by friction is the force of friction times the displacement, right? Times the cosine of 0 or 180, however you want to think of it. So anyway, you get negative 172.5 newtons times 6 meters, and it gives you negative 1,035 joules, and then I rounded it up to. Everybody good? All right. Are there any other forces doing work? There are other forces, but are they doing work? No, because all the other forces are Good, perpendicular to the motion, right? This is the other advantage to finding your components, because I can look at this little drawing that I shrunk too much. I know the motion is this way. This is all of my forces, right? And every one of those forces is either parallel or perpendicular. So all you got to look at is the parallel ones. Follow?
Yeah.
All right, so check it out. We're almost done. Here's what we're going to do. So our net work, that's the work done by Roy plus the work done by friction, right? Because those are the only things doing work. So that's, what am I done? 2078.5 plus negative 1035, and it gives you 1043.5. So that's my net work. We are almost done. Any questions before I go on? Yeah.
Just don't like a bunch of friends. Social network.
Sorry?
Just don't like a bunch of friends together. Is it social network?
Oh, I guess so. That's very good. Sure. Yes. I was slow on that. It's good. All right. Everybody good? That was good. Yeah, you had to work for it too. All right. All right. Is everybody good with how I found this? All right. Now, what does the network kinetic energy theorem tell us? That's my change in kinetic energy, right? And since, what was our initial kinetic energy, you guys? 0. So what's my final kinetic energy? 1043, right? If you start at 0 and then gain 1043, you're going to end at 1043, right? We're like 10 seconds away from being done here, so if I could get my board to work. All right, is everybody good with what I did here?
Yeah.
So now we can find the velocity, right? Yeah, that was question C. Everybody good? So 2 times 1043.5 joules divided by, what was it, 50 kilograms? Square root it, and it should give you, what did I say, 6.46? There you go. Cool? Yes. Say it again, I'm sorry, one more time.
Moving on velocity is so
You mean like before Roy's force? Is that what you mean? It wouldn't have been a constant velocity because friction would have been slowing it down. But if you were given an initial velocity, then yes, the only difference is that your initial kinetic energy wouldn't be 0. It would not be 0. So like if the starting velocity had been, say, 5 meters a second, that would mean that your starting kinetic energy would have been whatever that is. You keep saying constant. So are you talking?
So saying like without acceleration, this is
If the velocity was constant, then there would be no net work.
right. So what I'm saying is like the purpose of the problem here. It says it's starting in the process rest. But if it was starting in motion, that would give it the initial motion.
Correct. Pretty good?
Yeah.
If the problem, so when you keep saying constant velocity, are you talking about constant velocity before the problem began?
Yeah.
Okay. Then yes, then we're on the same page. Because do you see what I'm saying? After the problem, like if Roy's pushing it and the velocity is constant, then there is no network. Right? Because that would be telling you that the horizontal component of Roy's force is canceling out friction. Their net force would have to be 0. Good? All right, due dates.